Okay, we're going to work pathway 7.7. Now, this tells us that there's a radio station, an AM station, which stands for amplitude modulation. That's broadcasting at 950 kilohertz. What is the wavelength of the waves in meters, nanometers, and angstroms? All right, well, to help us figure this out, I think the first thing that we need to probably do here is interpret the problem, interpret the information. We're clearly asked for a wavelength of the wave, so maybe we're developing an understanding of what that means. But what's this 950 kilohertz? I mean, what in the world is that all about, right? Well, when you see this Hz unit, that's the base unit for hertz. Or cycles per second, which is s to the minus 1, which is really 1 over second. So we're counting the number of oscillations of this wave per second. In this particular case, it's 950,000 oscillations per second. So I think the first thing that we need to do here is kind of delineate, like, what is this number? What does it represent? And hopefully, as I've been talking about it here the past few seconds, you realize that the number that they're giving you is the frequency. Hertz, or per second, is a frequency unit. When you see that, you probably should think frequency, okay? So they give us the frequency of this wave and want us to find the wavelength. Well, how do we do that? Well, we do it through one of the most fundamental wave equations, okay? That is the product of the frequency times the wavelength yields the velocity of the wave. Okay. Now, for electromagnetic radiations, such as radio waves, we know that c, the speed of light in a vacuum, is a constant. 2.99 times 10 to the 8th meters per second. All electromagnetic radiation propagates through a vacuum at that speed. And for our purposes here, we're going to say that air in the atmosphere that these radio waves go through is close enough to a vacuum as it doesn't matter. Okay, which is the usual case for problems in this class. All right, so what we know then is we can solve for our wavelength if I can plug in a number for my frequency. Now, when I plug in a value for my frequency, I want to plug in the value in hertz units or in cycles per second, not in kilohertz or kilocycles per second. So I need to do what? Conversion. So I know it's 950 kHz. It's really easy to do a conversion because this is just a metric prefix, kilo, right? For every 1 kilohertz, there's what? 1,000 hertz. It's just the K, getting rid of the K. So clearly, I multiply my 950 by 1,000, and as a consequence, I'm dealing with a wave that's 950,000 cycles per second, or 950 hertz. You could also tell someone 950 kilohertz. They all mean exactly the same thing, right? All right, so then we're off and running to solve for the wavelength. I just take my C value, my 2.99 times 10 to the 8th meters per second, and I divide that by my 950,000 per second, seconds to the minus 1. Second units cancel, and I'm left with about 316 meters. That's my wavelength. Alright? So this radio wave has a wavelength of 316 meters. It's a very large wavelength if you think about it. Very substantial distance for one complete oscillation of the wave, right? Okay, so that is the answer in meters. Now, looking at this book problem here, they want us to also do some unit conversions to express the wavelength in other units, such as nanometers and an angstrom unit. I think this might be the first time you're introduced to angstrom, so we'll take a look at this. Okay, so it's just a unit conversion in either case. Okay, so 316 meters. If I want to convert that into nanometers from meters, I have to realize that there are 10 to the 9th nanometers in 1 meter. Okay, so I actually have to multiply this number by 1 billion, essentially, okay? And if I want to write it in scientific notation, it works out to be 3.16 times 10 to the 11th nanometers is the wavelength of one of these waves, okay? That's a nanometer units. If I want to convert the 316 meters into angstrom units, I can also do that. Well, this one's probably a little bit harder. The angstrom's given this little like A with a top hat, I don't know, angel symbol or something like that. The baseball team, the Angels, or something like that. But anyway, this is angstrom units. Now, angstrom units may be unfamiliar to you, but it turns out that 1 angstrom is 10 to the minus 10 meters. It's a distance unit. 1 angstrom is a tenth of a nanometer, basically. Okay, so it's even smaller than a nanometer. So as a result, there are 10 to the 10 angstroms in a meter. The meter units cancel. I'm left with my angstrom units. And my answer in angstrom is 3.16 times 10 to the 12th. Okay? So all these are correct ways to express the wavelength of this wave. 360 meters seems pretty convenient to me because you don't have this more complicated scientific notation. But I understand why your book asked you about to convert to these. It's so that you could do it. You're going to have to do quite a bit of conversions, I think, in this chapter to nano units or maybe angstrom units. So they wanted you to remember early on in the question sets that this was the conversion factor for nano and this is the conversion factor in angstrom, to be introduced and reminded of that. Okay, so that's why they asked you to do